This is the GNNLens interface. In the upper left corner, there is a control panel where you can make various selections based on the data you pass to GNNLens. After you select a graph option, GNNLens will start visualizing the graph. It uses a simulation-based algorithm to determine the node positions. You can stop the simulation by clicking the button here. You can drag on the plot. You can zoom in or zoom out on the plot. GNNLens visualizes node labels by node color, and you can click the drop-down list here to make an option. The drop-down list visualizes the available node label sources, which are typically ground truth node labels, or the labels predicted by some models. After you select a node label source, you can find the color legend in the lower left corner. Similarly, you can visualize edge weights by edge thickness by clicking an option. As you hover over the graph, GNNLens will display the associated node ID. If you click on a node, GNNLens will display by default its 2-hop subgraph. GNNLens provides built-in support for extracting and visualizing 1-hop and 2-hop subgraphs, with the selected center node highlighted here. The node label and edge weight options also apply here. You can change the node ID selection in the ID box here. GNNLens also allows selecting simultaneously multiple node label sources for a direct comparison. Once you select multiple node label sources, GNNLens replaces single-colored nodes by what are called NodeGlyphs. The center of a NodeGlyph is colored based on the first selected node label source, which is ground truth in this case, and the outer pie chart is colored based on the rest node label sources in a clockwise manner from the top. So this allows you to directly comparing the different node label sources in a single plot, and you can then tell one model here, which is GNNL2, has made a mistake in the node label prediction. GNNLens also allows you to pass some custom subgraphs for visualizing. For example, you can parse the explanations by some explanation methods, which are typically some form of weighted subgraphs. You can then find an associated option for this explanation. For example, you can select the integrated gradients explanation here for the prediction of node 0. Then you will see the associated weighted subgraph. In this case, GNNLens uses node color opacity to visualize the node weights. After you are done with examining subgraphs, you can click the button here to return to the global view.